Welcome everyone. Today we're happy to have Jorrit here. He's going to tell us about an integrable road to the Perturbative Plateau. Take it away.
Thank you guys. Thanks, Lawrence. So I just started here. So for everyone who doesn't know me, I'm Jorrit Kruthoff. I'm in office 193. If you want to talk about some stuff, come visit me. Right, so today I want to talk about a paper that came out recently with my collaborators Andreas Blommaert and Shunyu Yao. And it's about a curious limit of the spectral form factor that has some interesting structure that previously we thought that very long times needed non-perturbative effects to explain certain phenomena. We can now, within this limit, we can understand that perturbatively. And the reason why sort of that approach works is because of some integrable structure underlying the calculations of the spectral form factor. I should also point out that there was a paper that came out simultaneously as ours. It's in the more quantum chaos people in Regensburg, in Germany. And they also discuss similar aspects of what I will be talking about today. It's this archive number. And there is a different group at Stanford, by Saad, Stanford, Yang, and also Shunyu again, that discusses this, the thing I will be talking about yet from a different perspective. So you can, but that's to appear, so that we need to wait a little bit. And anyway, so let's talk about the spectral form factor. So the spectral form factor has a definition that I've written here, where Z beta plus IT is E to the I, sorry, it's a trace, E to the minus beta plus IT times H, where H is the Hamiltonian of your system. So this could be an object that you want to study in some random matrix ensemble, where these angular brackets are an average over different Hamiltonians drawn from some distribution. But recently, we can also understand this in gravity. So we can also understand these partition functions or this particular object as a partition function, correlator of two partition functions. And in gravity, that means that we have two asymptotic boundaries, and we consider all types of geometries in between. Wormhole geometries, disconnected geometries, higher genus wormholes, and all of those will play a role. But the connected components will play a role in my talk today. So if you plot the spectral form factor as a function of time, so you keep this beta, the inverse temperature, you keep that fixed, then it has a shape like this. So initially it has here an exponential decay that goes over into a power law decay. Then it dips down, and from this point onwards, it develops, it has a linear behavior with some corrections, as we will see. And then famously, it goes over to a plateau. And that means that at large times, in this particular correlators, the eigenvalues need to align in order to get a non-zero answer in the double sum over eigenvalues. Now, geometrically, and so from the matrix model, we can calculate this rather precisely. In geometry language, this initial part comes from the disconnected component of this correlator. And from this point onwards, where the sort of this point is called the dip, from this point onwards, you're getting connected contributions that that result in an increase, and those are the wormhole type contributions. So there's these type of wormholes, but there's also wormholes with various genera that that contribute. And then in the end, at very large time, so the geometric description is a bit ill-defined. Or sometimes you need to include everything, and there's also D-brain type effects that play a role. So that's all you need to know about right now about this spectral form factor. And what I want to do is to analyze the spectral form factor first from the matrix model, and then analyze it from the gravity. So I'll explain what type of limit I will be taking of this spectral form factor in order to access this plateau, and this region is called the plateau, to access that perturbatively. All right. So let's write out this this spectral form factor in energy space. And so you can write it this way. And here we would have two density of states factors. And here the angular brackets mean that, so I'm going to focus on the connected component, and the angular brackets mean that I'm doing this an average in a matrix model with some potential for this Hamiltonian H. And right now that could be anything. And now the limit that I will be considering is I want to take the time, so that's the this parameter here. I want to take that to be very large. That basically tells me that the difference in energies is very close. And so the difference in energy is very small. And in that case, there's a general formula for this rho correlator. And it looks like this. So in that limit,
excuse me, could you try to stay on the left more for those watching the Zoom? Unfortunately, we can only see 1/3 of the way to the right of that screen you're on now, right? The middle blackboard.
I don't think I have control over that, no?
That's why I'm suggesting you could stay more on the left.
Oh,
Right on that side.
you want me to stay? Oh, okay.
Well, maybe it's inconvenient for the live audience. I don't know.
Yeah. I can do that.
Okay, Jorrit, you can write on the.
Okay, but now I erased everything.
I'll control it. You can first. I'll try to catch up with you.
Sorry?
I'll try to catch up with you. I think that I can.
Oh, yeah, and you want to do that? Okay, sounds good. Well, okay, then let's try this again. So this was this double integral. And this guy we can, in this limit where t is very large, this is only part of the limit. I'll tell you a little bit what the other parameters that we're taking large. This is This is the famous sine kernel, it's called. And rho naught here is the average density of the eigenvalues in this particular matrix ensemble. Right, and usually what we do is that in order to connect back to gravity later on, this rho naught will have a particular parameter. E to the S naught, it's usually called, it's very convenient from the gravity point of view. And this particular parameter is a genus counting parameter. So that enters in the matrix model in a way we call double scaling. And this factor enters, it's sort of the number of eigenvalues that are present. Since you scale that to infinity in the double scaling, there's a finite parameter here that we're taking into account. And that we call e to the S naught. And then there's a function of the energy here that right now I don't need to specify. But now the second part of the limit is that we're going to take e to the S naught also very large. So we're keeping the ratio. We're keeping that fixed. And this particular limit is often studied in random matrix theory. And it's called the tau scaling limit. So with this, with these limits, you can calculate the spectral form factor exactly. And but essentially, this only depends on the difference of energies. So you can do this integral over this Fourier transform of that function explicitly. And that's actually giving that sort of that ramp and plateau type feature that I drew there. But the answer is rather simple. Some simple manipulations using the Fourier transform of that sine function. And where E of rho naught is the inverse of this function, this density of states. I can also, since rho naught contains this factor e to the S naught, we can also factor that out. Write this in a more convenient way. Right, so within this limit, the spectral form factor reduces to this rather simple expression. And this simple expression right now, what I used here is I used the matrix model description and the matrix model universality, this formula for the rho correlator to arrive at this formula. Now, the interesting point here is that, well, first of all, notice that when t goes to infinity, we're just getting back the value. Here a couple of points. When t goes to infinity, we get the asymptotic value of the spectral form factor back. I think I drew that there. That's z of 2 beta, so that's the plateau value. And furthermore, what you can do is you can develop this into a power series in T, or in this parameter tau. And then you'll So you can write as a power series where there will be some function of beta. But sort of interestingly, there's this power of time that's fixed. It's 2n plus 1. And will turn out, sort of gave it away already, but the n here is going to be the genus in the gravity calculation. And what this power series is really, and looking at this expression, the power series is really an expansion at small energies. And so we're very close to where the density of states is very small. And we're probing, sort of draw what this density looks like. So this density often looks something like that, can grow, but it has a square root edge behavior, and then there could be e to the 3 halves, etc., 5 halves, 7 halves, etc. And this power series, what it does is the first term sort of probes the this part, and then the higher order terms probe higher order terms in the density. So there will be it probes more of the UV of the spectrum. Another thing is that so here I've used, this is all very general, so this holds for any matrix model, so in particular we can study some simple examples that I think will be nice to solve. Another point here is that if you do this power series expansion, depending on the model that you look at, this power series expansion has a finite radius of convergence. And so that's sort of the perturbative, that you have perturbative access to this plateau. There's no need for non-perturbative effects to come in. Right. So let's study two examples. So one I will call the Airy model. The Airy model is very simple. It's where you only have this square root. And we'll have an expression like this. And so to calculate this, what we need to do is invert this relation. This square. And then the spectral form factor in the tau scaling limit. I should put like a tilde on here. So tilde would be this tau scaling limit. This guy you can very easily calculate that this is going to be a Gaussian integral, but at some finite range. And so you're getting some error function here. Here. Beta t e to the minus. Okay, so this is the exact answer that you get in this particular limit, and you can develop this into a series, and you get various terms. Etc. And this particular expression, the radius of convergence of this series is infinite. This converges for any t. And so this, you see that you have a perturbative access to Okay, maybe I should just plot this function. This function has a form that looks like this, where there's a particular plateau value, and this power series with the linear term in T in gravity, we think about that as just the usual wormhole. And actually these higher order terms, they will be higher genus wormholes. The genus 0 approximation is just linear, and you have the cubic, and then T to the 5th, etc., etc. Now, and to connect more to gravity, let's also do the example of JT. In JT, the density of states is this. The famous Schwarzschild density. We can again calculate this spectral form factor. We invert that relation. But in this case, the radius of convergence of this series is finite. So in that case, you get a just like T e to the minus S naught. That's then 1 over 2 pi. So for these values of tau less than 1 over 2 pi, you get the exact expression by just studying the series. And then you can just continue to larger values once you have obtained that expression for those smaller values of T. So again, you have a perturbative access to the plateau. Should note that the series expansion for this JT will be exactly the same for the first two terms, but for the higher order terms, there will be this function, this P, this polynomial. This will be more non-trivial in the case of JT. All right, so this was purely from the matrix model side. Now, what's the goal for today? Or the goal of the paper that I wrote with my collaborators is to understand this particular this tau scaled spectral form factor from gravity. So what we want to do is to obtain actually this power series. And an interesting result already is that this is true from the matrix model, that would suggest that from the gravity side, we don't need any D-brane type effects to understand the physics of the plateau. Let me also mention the results. The key takeaway messages. So at each genus, you get a contribution that goes like T to the 2G plus 1, regardless of the dilaton gravity that you're considering. And the reason why you get only these powers is you might expect, I'll come back to that these powers can be higher in principle, but the power of T is bounded because there are certain relations in the Val-Petersson volumes that you use to calculate higher genus corrections to the spectral form factor. And why are there these relations? Well, these relations actually originate from an integrable structure in all 2D gravity theories. This integrable structure, these are the KdV hierarchy, KdV equations. Another thing is to understand this perturbative, the fact that you have this perturbative access to the plateau. And that is because in this particular limit, this tau scaling limit, you only care about certain parts of the Val-Peterson volumes, or you only care about part of the moduli space. And the parts that you throw away are precisely the parts that grow factorially with the genus. So get rid of and those 2G factorial terms are also famously responsible for D-brane type effects, but you just get rid of those in this particular limit and result in this finite radius of convergence. Okay, any questions at this point? So let's go to the gravitational calculation of the spectral form factor. I told you that the spectral form factor in gravity, we think of that as a correlation function of partition functions. And in gravity, we think about that as two circles. So we do the calculation in Euclidean signature. We have a beta 1 on the left and then beta 2 on the right. And then we draw all the contributions to this observable, so to all contributions subject to these boundary conditions. That would contribute in the path integral. So we would have just the usual wormhole, but now at higher genus, you can also have any number of holes here. So this, if these would be G of these holes here, this would be a contribution to the spectral form factor. I'm going to introduce some notation here. So here Z sub G means the genus G contribution to the two boundary observable in gravity. So I have a beta 1 and the second argument is beta 2. Now the way to calculate this object, I think many of us know, is by cutting this surface in a certain way. So we can cut this. So this is an asymptotic boundary right here that has renormalized length beta. We can cut the geometry here at a geodesic, and that's this geodesic happens. This cut happens before any of these higher genus contributions are present. And then we do the same thing on the other side. And well, these guys we call trumpets. And then this piece in the middle has two geodesic boundaries and has genus G. And this is a bordered Riemann surface And in the gravity calculation, we need to include all possible shapes of such surface. So we need to find the volume of moduli space of these particular surfaces where we keep the lengths of these geodesic boundaries fixed. We'll denote these geodesic boundaries by B. And then the this particular contribution can be calculated as a form. So this contribution, this is the volume of moduli space. That's this middle part. And then we have these two trumpet partition functions, and you can calculate them. And they have an expression like this. These volumes, there are two things that are important here to know about these volumes. One of them is that they're polynomials. In BI squared. So they have a maximum degree. It's 3G minus 1. And this is particular for, so this 2, by the way, stands for 2 boundaries. So this is all specific to 2 boundaries. And so we can write an expression for these volumes in this way. B1, B2. So these volumes have an expansion, polynomial expansion in this way, and these VG, just the coefficients of that. Now to get to our calculation of the spectral form factor, what we do is we send beta 1 and beta 2. Send these to beta plus or minus IT. So that's coming back to the expression I wrote down in the beginning. So now we want to study this particular contribution at large T and when e to the s naught goes to infinity. Should probably put in here that factor. So there's here a factor of minus 2G s naught. This is the Euler character. All right. Now, so I told you in the beginning that these powers of T are constrained to be 2n plus 1. There, we saw that at each genus, the power should be 2g plus 1. But now with this expression that I just wrote, that raises a little bit of a puzzle because I told you that the maximum degree is 3g minus 1. So when you do this integral and you stick in the maximum degree, you get something where you get a polynomial again in beta that has a maximum degree of 3g minus 1. So that would, let me just write that down. There's a puzzle. You seem to get That's by doing at these integrals. You should be able to get a power 3g, t to the 3g. Is it when you do it like that? That just follows from dimensional analysis. But you expect t to the 2g plus 1, given the matrix model answer. So now the question becomes, okay, if we, how do we get rid of all those higher powers? And that suggests that there are particular relations between these volumes, these coefficients here. So that's also the correct answer, is that there are cancellations. Amongst these terms. For example, say we look at genus 3, and this D2, genus 3, and this D2 is 8 minus D1, and so we would have a contribution like this. These signs follow from the analytic continuation with these eyes there. Now these particular coefficients, you can find them, say we're in JT or any other dilaton gravity that you would like to consider. You can calculate these. So I think, for instance, this for JT, you get some funny numbers. I'm just trying to tell you what sort of the non-trivial part is of these relations, is that you get all these crazy numbers. And so when you add these guys up, you'll get 0. And so sorry, this is not, this is 8. And I think this is for the power t to the, this will be t to the 9, something like that. You'll get like some crazy numbers. When you add them up, they magically cancel, and you don't have that t to the 3g power. And similar relations also exist for lower order terms, until you hit this guy, and that will be non-zero. Now to prove such a statement is rather complicated, but there's actually a nice way of thinking about it. And that's something that I sort of 3 ideas that you can use to prove this statement for all genus. Let me use this board.
So question, where does the -1 to the D come from? Why do you need that factor?
Yeah, that comes from you put in this beta plus IT. These i's give rise to that that -1 to the D. Right, so there's essentially 3 ideas that you can use. So first of all, these volumes, they're related to intersection, what's called intersection numbers. We won't need much of what these intersection numbers precisely are. But what I want to stress, and I'll go over some examples that will make clear what I mean with these guys. So these coefficients, they actually have a separate mathematical definition. And that's these intersection numbers, and they're usually denoted in the following way. These taus are certain forms that you integrate over the moduli space. And then here, I'm going to do a slightly unconventional thing, but nevertheless correct. So these are related to certain integrals over the moduli space of genus G Riemann surfaces with n punctures. And then we have
the n on the right-hand side is not the same n as on the left-hand side, right? Because if you expand the exponential, you get more taus.
That's right. That's right. So what I mean here with this expression, this is more like a closed string expression, where this guy, when you expand it, then these ends are not the same. But the whole purpose of this particular term is to deal with more general dilaton gravities. And so in the case of JT, this would have a particular form, and then you would integrate on this moduli space with some extra factor. And indeed, when you expand the exponential, you get different ends. Okay, so that's one thing. So these coefficients have a separate mathematical definition. And then the statement is that these intersection numbers they satisfy, famously, they satisfy the KdV equations, or rather the generating function of these guys satisfies the KdV equations. So let me just write it like that. This should be thought of as the generating functional satisfies the KdV equations, and that puts constraints on these correlators. And the third point is what Lawrence already elaborated on, is that usually these intersection numbers, we think of those as, in the case of what we call topological gravity. And so that's this Airy model that I discussed, where you just have the square root edge density. But if you want to study, say, JT or some more general dilaton gravity, you would need to modify these intersection numbers a little bit. And you can either do that in this way, where you insert this exponential. That's like a closed string perspective, but it's rather complicated to calculate this directly like this. What you would do is expand this exponential, and then you would get the ordinary intersection numbers back, with an infinite sum of those. So that will be in that's an open description, where indeed there will be more and more boundaries. So the other thing is all right. So for instance, for JT, these gamma k's have a form like that. That's just giving you the specific density of states that you need for JT gravity. If you pick this particular choice, then this exponential is also what's inside the exponential is a known object. It's the Val-Petersen volume, or the Val-Petersen 2 form. The symplectic measure on the moduli space of closed surfaces or punctured surfaces. Okay, so maybe we should try to see what these KdV equations are in a bit more detail. For that, I want to go back to this Airy model. So in matrix models, we call this the Airy model. In gravity, we call that topological gravity. Density of states is given like that. And now, well, the question is, within this topological gravity, how can we understand these particular relations, this KdV? So if we study, so the contributions can still be calculated in a fashion like this. But in the case of JT, you'll put the Val-Petersen volumes here. In the case of topological gravity, you'll put slightly different volumes here. And essentially, I mean, that also follows directly from the topological recursion that you can do using that density, using the Einhard-Orentin recursion. So let's look at what happens for one boundary. There'll be a simple warm-up. Then these volumes, let me put an A here for Airy. They have a form like this. And then you can write them in terms of these intersection numbers in this way. Okay, so these volumes are written in terms, so that's point one. The second point, and I mean, the first point is just a rewrite, but the second point is the important one, is that the generating function of all these correlation functions of the taus that satisfies certain equations. So if I write, say a Z, there's only this one. So Z is the generating function for all correlation functions, connected and disconnected. Here F will be the correlator for all connected guys. And the statement that they satisfy this KdV equations is simply the statement that Z is a highest weight factor of the Virasoro algebra. LM here are the generators of the Virasoro algebra, and so they have the usual commutation relations. And these LMs are differential operators with respect to these TKs. So here you can understand that when I take derivatives of the TKs and set the TK all to 0, that I can get a certain correlator. And these LMs, they have a certain definition in terms of those TKs and their derivatives. For instance, if in the case when n is -1, and this guy has the form so this L has a L -1 has this definition, and similarly for all the other m's, there's just an algorithm to get those. But the point is that this generating functional satisfies this particular equation, and there's an infinite number of equations, and they all constrain the form of these correlators. They all constrain the form of these tau correlators. In particular, in this one boundary case, we just look at the 1-point function, you'll find a relation that looks like this. Okay, so this is a relation that needs to be satisfied. You can use this. You can transform this into a differential equation. For instance, if we use a notation, right, g of beta this way. X beta. We expand, we write this f as in this particular expansion, then we can turn this recursion relation on the taus into a differential equation f, and that results in a particular expression for f.
-3g.
Yeah, you'll find that from this recursion relation that.
Because for n not being multiple of 3, this doesn't make it.
Yeah, that's right. That's right. I mean, then it's just 0. Yeah. Essentially, that you put in like a boundary condition to ensure that those are, and that you know beforehand. So this f has a form with some constant. Like that. And this constant is equal to 1. Turns out that's related to that you can separately calculate using this math definition. That this tau1 correlator or a genus 1 surface is 1/24, and that sets this constant c to 1. And so from this analysis, you'll find a particular expression for this correlator. And well, this was just to say that similarly for the 2-boundary case, you can again do this calculation, and you can again write a similar expression for this f. These ADV equations again give you recursion relations, but they will be more complicated. The differential equation will be more complicated. But in the end, you'll get an expression if we write down a similar expression for this curly f. get an expression like this. And then you can check that when you expand this this function, that there had to be relations amongst the different intersection numbers. In this case, you would have intersection number with two of these taus inserted, and that would result in so the fact that this has a particular form that you found from the differential equation or from the recursion relation. It also means that these taus have a particular relation amongst each other. So this is only non-zero. D2 plus D1 is 3G minus 1. And yeah, so there's particular relations amongst the different taus. Sort of the cleanest way of seeing the relations and the maximum power of t is to write this functions f or any coordinate that you want in symmetric polynomials. And so you write them in elementary symmetric polynomials. For instance, in this case, you would write E1 is x1 plus x2. E2 is x1 times x2. And then the statement about this maximum power of t becomes a statement about the maximum power of E2. Because x1 and x2 are proportional to beta. So this will be proportional to t squared plus. When we analytically continue, this will be proportional to beta. And so here we can just focus on E2, and we find that that there must be a constraint on t, on this power of E2. So there was a very nice work by Einard, Lewansky, and Ohms, I think a year ago, where they precisely studied this question. They precisely studied why is it that if I write and they also work with this curly f, if I write that in terms of these elementary symmetric polynomials, why is it that you only get certain powers of these symmetric polynomials? And they had a way of proving that and analyzing that essentially for any number of boundaries, not only a relation for this two boundary case, but actually for any number of boundaries. And since you have this result for any number of boundaries, you can use this open-closed duality where you think of JT gravity essentially as a deformation of this topological gravity. And then you would basically be forced to study correlators of more and more taus involved. And what this result by Einard, Lewansky, and Ohms tells us is that even if you do that, the maximum power of t is still through 2g plus 1. So the maximum power cannot grow more. Part of the reason is that if you want to study a true boundary observable in JT, you have two of these taus inserted, and it's 2 in that case. And then you have this exponential inserted, but it's inserted with it's coupled to this gamma. This gamma is just a number proportional to pi, the only way the b dependence or the beta dependence, the time dependence can come in is by these first two factors. So that tells you that even if you have higher order symmetric polynomials, only those guys can only grow with t squared and nothing more. I think I'm already over time, right?
Yeah.
Okay. All right. So maybe I can just explain that a little bit more. So if you have these n number of boundaries, you would have an expression, you sum over the genus. So using these symmetric polynomials, e1 to the m1, e2 to the m2, etc. And then here there will be some coefficient CG that depends on the m's. And what Einard et al. Showed is that these CG these are 0 whenever this condition is true. So when the sum of all these mj's, when m with j bigger than 2, bigger or equal, these coefficients are all 0. Now, and how does that help in the case of JT? Actually, any dilaton gravity. So let's write spectral form by the Euclidean purple. Let me write U here for any number of dilaton gravity, dg. And this F dg, we can write that in terms of these intersection numbers the following way. It's similar to what I wrote already for the one boundary case. Then we have this guy inserted. There's genus G. Now, if you introduce a variable like this, these are just arbitrary variables. And you can expand this guy in the following way. That's basically the open-closed duality that I'm using here. X1, X2, and then I have these bunch of Y's. Like that. And so I traded this exponential to an insertion of extra boundaries that I labeled with y1 up to yn. These y's do not depend on beta or whatever. They're just numbers that you can find by solving this relation, this and that. The only dependence on t comes from this x1 and x2. If we then go back to this particular expression, these symmetric, elementary symmetric polynomials, it means that so E1 is a sum over I of all these guys. x2 plus y1. And then for E2, there will be products of two elements. And E3 will be products of 3, and then you sum over all possible combinations to make it symmetric. But what you'll find is that E2, if we take T very large, which is the goal here, then E2 would would go like T squared. E3 would also go like T squared. And actually all these EKs will go like T squared, except for the first one. And so if you then look at this particular formula, if all these guys going like T squared, what that means is that the power of T will be just the sum of these n's. And then there's one more power of T that comes from a factor like that. And here we saw that all these coefficients where the sum is bigger than G, they're all 0. But the maximum power here is T to the 2G plus 1. Yeah, so that's a way to prove that the spectral form factor has this power series in G, and then we can couple that to the fact that then you don't have this 2G factorial growing terms. You get a nice convergent or series expansion with a finite radius of convergence. Yeah, let me stop here.
Any more questions for Jorrit? Maybe I can ask the first one. So you didn't really explain why there are no 2G factorial growing terms there. Is it obvious, or I mean, from what you said, it's not clear. You just explained that the higher powers of T cancel that.
Yeah. So the 2G factorial terms. So in the Airy case, so the topological gravity, there are no 2G factorial growing terms. And then you can ask, okay, can we generate 2G factorial terms from inserting this exponential? And the answer is yes, you can. You can generate these, but they since, and what you already mentioned is that you have these extra number of boundaries. They will only contribute to parts of the polynomial where you have a lower degree. So this T to the 2G, what it picks out in the volume is the maximum, sort of the largest degree polynomial in that volume, at least for the Airy case. In JT, there are some subleading terms that also contribute. And so the terms with the highest numbers of D1 and D2 that you could have, they contribute to this particular spectral form factor and perhaps some subleading terms. But the 2G factorial terms, they are present in the in part of the polynomial that's just the constant part, or the linear term. Those grow very, very fast. The others. Thanks.
Any other questions?
Is there a generalization to one possible more boundaries?
It doesn't seem there's a nice generalization of this this particular tau scaling limit to more boundaries. No, it's because you have multiple time arguments, and it's not clear what type of limit you would like to take. Let me say, in the matrix model, you can write down a simple expression, like the one I wrote in the beginning, but that sort of has the wrong scaling with e to the s naught to map onto some nice gravity calculation.
What is the meaning of the like in JT gravity? You get finite radius of convergence. Is there like some singularity somewhere in the complex plane? There's some physical significance.
I don't know. Yeah, I don't know. I mean, the thing is that you, in that case, the density is like a singe, and you invert that relation. That function has a finite radius of convergence. That has a branch cut. Essentially.
Yeah.
That's it.
Right. Any more question for Jorrit? Otherwise, let's thank him again.